elements that occur in nature. Most of our 4,000 minerals are going to contain one or more of these 8 elements, simply because they're the ones that are most common. That makes it very useful because then we can look at those 4,000 minerals and we can break them up and subdivide them into groups or categories based on their general composition. This gives us several mineral families, mineral classes, or mineral groups. They go by a lot of names. Now, there are about 15 of these mineral classes. Of those 15, there are about 8 that you're going to see most often. And I'm not going to put, that's a nice bracket. I'm not going to, that's what your calculus does for you. It helps you to draw these things. It's like I need to put a dx, dy here. Now, I'm not going to put these in any special order or anything like that, but just as I remember them off my head. So, we'll start with these. So we're going to do those. And then over here, Let's start with those. So about 15 or so mineral classes. These 8 are probably going to be the most common. You'll see these the most often. These are definitely the 8 classes of minerals that you'll see in lab in the next 3 weeks. We have native elements, oxides, sulfides, halides. And we have sulfates, carbonates, phosphates, and silicates. Native elements. Now, most minerals are going to be compounds. That means they're going to be made of at least 2 elements bound together chemically. Now, in some cases, you can have elements just all by themselves. For example, gold. You can find just nuggets of gold. You can find nuggets of silver, nuggets of platinum. You can find elemental mercury by itself. You can find sulfur by itself. You can find carbon by itself in the forms of graphite or diamond. Those are native elements. And gold, diamond, copper, sulfur, mercury, list goes on and on. Graphite, you saw in lab last week. Those real gray, shiny, real soft, greasy, peeling rubs off on your fingers. Mineral from last week. That was graphite. That's carbon. That's a native element. The only diamonds you're going to see in lab are ones you wear and bring yourself. We don't have any. We had one time, we had bought this beautiful, they sent us a beautiful specimen, of a fool's gold iron pyrite. And Friday we set them out on the cart to the lab, and we came back and Monday they were gone. So, yeah, we don't have any diamonds in this room. So, let's see, oxides, sulfides, halides, that IDE E ending is telling you there's a metal, a metallic element present. So if we start with oxides, that's going to be the element oxygen bound with one or more metals. Then we have, that's corundum. Corundum is an aluminum oxide. Corundum is a fairly common mineral. Red varieties of corundum are known as ruby. All other colors of corundum are called sapphire. The different colors come from other metals that kind of get stuck in there as it's forming, and they impart a little bit of color. Other important oxides are hematite and magnetite. Both of those minerals are iron oxides, and they are and have been throughout history extensively mined for their iron. Sulfides are going to be sulfur plus one or more metals. Most of our industrial ores are sulfide minerals. They often form together under the same conditions, which is really convenient for us, because if that means then we find one, we probably get a lot more around the same area. Salarite, and galena, pyrite, chalcopyrite, bornite, arsenopyrite. Oh, it just goes on and on. I'm trying tonight. This just goes on and on. Salarite is zinc sulfide or zinc. Galena is lead sulfide. Pyrite is iron sulfide. Chalcopyrite is iron copper sulfate. Chalcopyrite sulfide is the world's primary source for copper. Main ore for copper. The neat thing about chalcopyrite is it forms at specific temperatures, and it's often also associated with gold. So often look for chalcopyrite as a gold indicator. Salarite is also often found with nickel and tin. Galena is often found together with platinum and silver. So a lot of times if you have like a lead mine or you have a zinc mine, they'll process those other metals at the same time, kind of as a side business. Because every one of those metals melts at a specific temperature. So they take the ore, they crush it, they crush the rock to get the mineral out of it, then they crush the mineral, and they put that crushed up material in a big furnace, and they just dial up the furnace to however hot they need it to get the zinc to melt out. And then they pour that on the top, and then whatever's left, well, they reset the temperature and melt out the nickel, melt out the silver, and then they go through purification. Unfortunately, when we process these materials from the metals they contain, that sulfur is released to the atmosphere, and it produces significant amounts of highly sulfuric rain. In the past, we didn't have the environmental controls over that we do today. But today, that's heavily mandated, and operations have to remove that sulfur and prevent as much of it as possible. We're not only getting into the atmosphere, but we're getting into soils, groundwater, and local surface water as well. That can make mining very expensive. Any questions? Well, then we have the halides. The halides are a metal, one or more metals, with what's known as a halide element. Now, again, this is just in the back of your book in the appendix, your handy-dandy little periodic table of the elements. So on A2, right at the beginning of the appendices. Now, in this periodic table, you notice there's some yellow elements here on the far right. The very last column of yellow, those are your halogen elements. Chlorine, chlorine, bromine, iodine, and astatine. By far the most common are the first two, fluorine and chlorine. Fluorine and chlorine are used extensively in the chemical and electronics industries for the manufacture of high-potency acids. Hydrofluoric acid is the strongest acid known to man. It's used to etch glass and circuit boards. That's some other chemical uses. Chlorine-based hydrofluoric acid comes in a wide variety of strengths. What you're using here in lab is hydrofluoric acid, very diluted, very weak. Some of the strongest hydrofluoric acids used in the chemical industry. It's also used in the pharmaceutical industry. It's used in construction. Muriatic acid is highly concentrated hydrofluoric. It's like dissolves concrete. Very well, very quickly. Dissolve your hand much the same way. Careful with that. No, it smells. Thanks. Go ahead. Horrible. It pass out. Well, see, the thing with hydrofluoric acid is that it goes to a gas very quickly, so it's in high concentration. And when it gets in contact with your skin, it turns back to an acid, and it causes acid burns on your skin. If you inhale chlorine gas, it'll kill you. Primarily because it mixes with the moisture in your lungs and produces concentrated hydrofluoric acid. Your lungs dissolve and you drown in your own blood. Yeah, just so I want to go. Yeah, sure. So that's a halide. The halide element with one or more metals. Okay, spell, man. Spell like the wind. It's not rotten most of the time. So it's a halide element with one or more metals. Some of the most common are going to be the minerals apatite, fluorite, halite. How do I forget that? Halite is another halide mineral. Halide is NaCl. Na is sodium, that's your metal. Cl is chlorine, that's your halogen. That's sodium chloride, that's regular table salt. Most of your salts are halides. You have potassium salts, magnesium salts, calcium salts, sodium salts. Any questions? Those are your halides. Well, then we move on to the eights. Sulfates, carbonates, phosphates, silicates. ATE in chemistry is telling you there's oxygen present. So all of these four, along with other elements, have oxygen in them as well. So the sulfates, we have oxygen. That's our ATE. What else? Sulfur. And one or more metals. Gypsum is a sulfate. It's a hydrated sulfate. In gypsum, the metal is calcium. It's CaSO4 with water. It's got water in its molecular formula. Its atomic structure contains water. Gypsum is used in the agricultural industry. It helps acidify soils to bring down the pH. Some plants like that. Gypsum is also used as a soil in soils to help break up clay. They make the soils more loose. It's used in all kinds of construction materials. You'll find it in wallboard and cement board and drywall and compound. Sometimes it's used in paints as a pigment. It's a white pigment. It's used in plaster of Paris. It's used in all kinds of things. It's used in a lot of pharmaceuticals. The carbonates, 8, again, you've got oxygen present. What else? Oxygen, carbon. This is really scratchy. So the most common are going to be calcite, dolomite, calcite, CaCO3. The metal in calcite is calcium, C for carbon, O for oxygen. Dolomite is calcium and magnesium. Two of those. Calcite, dolomite, see what else we got? We got azurite, malachite, those are copper carbonates. We have siderite, it's an iron carbonate. We have rhodochrosite, a manganese carbonate. Let's see, I can't remember. Celestite, lead carbonate. So we have a lot of different carbonates. Many of them are mined, especially calcite and dolomite are mined for construction purposes. We make cement with these materials, like cement, cinder block, concrete, drywall, dry compound, fillers. Dolomite's used when you need strength because the magnesium has strength for that. Let's see what else. Malachite, copper, it's mined for copper, big stuff. And it's also used as an indicator of a copper deposit. Phosphate, silicate. Phosphates, again, 8. It's definitely got oxygen. Oxygen, phosphorus, with one or more metals. What's a phosphate you guys see in lab? You guys seen phosphates in lab? Not that I can remember.
Looks like soda ash. Is soda ash that?
Soda ash is it's not a carbonate. I think it's it's derived from a halide.
Is it?
Soda ash is I'll have to look that up. I don't think it may not be considered a mineral. It's produced by human activity. Yeah. Why did I tell you apatite was a halide? Never mind the man behind the curtain. Yeah, I'm still. Gosh. This weekend was awesome. Wasn't it awesome? I had a day off. We don't get another day off until November. Veterans Day. Yeah. You got it. Yeah, apatite is another a calcium phosphate. I know why I put apatite in there because it can also contain chlorine. Apatite is a calcium phosphate. It's generally what it's kind of weird to call apatite. It's generally what your tooth enamel is made from. And apatite also contains the element fluorine as well as the metal calcium. And it's actually the fluorine that helps make it a higher hardness. That's why they fluoridate your toothpaste and your water. They're trying to add more fluorine to your tooth enamel to increase its hardness, to increase the resistance of being scratched for your enamel on your teeth. Yeah, that's a phosphate. It's a CaPO4. CaPO4. P is your phosphorus. And then last but not least, you have silicates. Silicates, again, are going to be your oxygen. 8 oxygen. Silicon. And one or more metals. That's going to be quartz. Quartz is a very common mineral. It's silicon, gosh, it's SiO2. It's the most simple of the silicates. In this case, your silicon is doubling as the metal. The various colors of quartz come from little impurities, other little quantities of other elements that get stuck in here and add color. Sometimes the same element can give you several colors based on temperature. We have quartz, we have feldspar. Feldspars can have aluminum, calcium, sodium, potassium. Those are their primary metals. Clay minerals. Clay minerals are silicates. Clay minerals can contain iron, magnesium, potassium, calcium, sodium, aluminum. There are some clay minerals that contain all of them, along with silicon and oxygen as well. The micas, mica family, the biotite mica, muscovite mica, talc, plotophyte, phyllite, and there's a list. Micas also contain numerous metals, especially iron and magnesium. Aluminum, along with silicon and oxygen. Any questions? Not colorful, nothing else. Now, of these 8 mineral classes that are on the board, of the 4,000 minerals, those 4,000 minerals, which of these 8 mineral classes do you think has the most minerals in it? One vote for silicates, one vote for sulfates. Anyone else?
Silicates. Yeah.
Okay. All minerals of the silicate mineral class must have oxygen and silicon in them. What are our 2 most abundant elements by weight in the crust? Oxygen and silicon. About 75% of all minerals are some type of silicates. And then, because silicon and oxygen are the 2 most abundant elements in the Earth's crust by weight. Most of the minerals you'll see in lab are some type of silicate. Most of your precious and semi-precious stones are silicates. Quartz, of course, includes all your amethyst, your citrine, your braziolite, your rose de France, your all of your chalcedonies and your agates and your jaspers. Those are all quartz. Moonstone, sunstone, those are labradorite. Those are all feldspars. Your beryl, your emerald, your aquamarine, your heliodor, your morganite, your what's the name of the other one? Your topaz. Those are all silicates. Very close second, oxides. Oxides are the second most abundant mineral class. The rest make up about 15% of all minerals. Any questions? So we have elements, and elements combine in different ways to form compounds or minerals. Minerals combine in various ways, in various proportions, to form another substance, and that substance is rock. So from minerals, we get rocks.
What would be an example of oxide?
Hydroxides? Most hydroxides hydroxides result from the exposure of other minerals to being outdoors, exposure to changes in temperature, the atmosphere, and water. By far the most common would be bauxite. Bauxite is an aluminum hydroxide. It's a breakdown of concentrations of aluminum in tropical soils, and it can actually be concentrated enough to be mineable. That is the world's primary source of raw aluminum, is bauxite deposits in tropical soil. There are a lot of other types of hydroxides. There aren't really a lot that you guys will see in the lab. Many of them are combinations with other mineral classes, like, for example, mica is a hydrated silicate. So, water or OH, oxygen with hydrogen, show up in a lot of minerals. They show up in a lot of minerals. I don't think there are any other hydroxides that you'll see in the lab. I mean, there are hydroxides, there's other hydroxides of copper, there's calcantite, there's words you'll never be able to pronounce again. I can't pronounce it. Yeah. And most of them aren't mined, but they're used as indicators of where mineable substances are. Because again, they result from being exposed to the air and the outdoors. So if they're on the surface, then they got to be coming from something underneath. Any other questions? So these make rocks. Rocks. Combinations of one or more minerals sediment, glass, or organic matter. Now we can look at rocks and break them up into categories based on how they form. And we come up with 3 categories. So we have 3 major types or classes of rocks. We have igneous, sedimentary, and metamorphic. Igneous. O-U-S, os means of, from. Ignea means fire. So when you turn your key to the ignition, the word ignition translates into making fire. And that's what you're doing. You're turning the key, and that's telling the battery to set a charge to spark plug, so the spark plug zips that, it's telling the fuel pump to put fuel to the fuel injector, and the fuel injector goes into the chamber, and that's hitting the spark, and boom, it explodes, it just goes up. Wheels turn, there you go. I'm going to miss that when we all go to hydrogen fuel cell. So igneous. Igneous means of fire, coming from fire. Igneous rocks form from the cooling And eventual, because this could take a while, solidification of molten rock. That's igneous. They're referred to also as being fire formed. They result from the cooling of the material that was originally very hot. Sedimentary rocks. Sedimentary rocks formed from the deposition, accumulation, and lithification of loose sediment. I need to clean these erasers too. Beat that to death later. So if you have rock, and over time that rock is battered by being out in the weather, it gets broken down into little itty bitty pieces and pebbles and particles of sand. Streams and rivers can move that sand to another location where it can pile up and become compressed and eventually become a sedimentary sandstone. This planet's not going to let anything go to waste. If you're going to have a process somewhere that's going to take rock and break it into pieces, there's another process somewhere else that's going to take those pieces and build a new rock with it. And that's what sedimentary rocks are. They're made from the bits and pieces of broken up older rock. Here you have metamorphic. Morph means shape or form. Meta means change. So metamorphic are changed form rocks. They're rocks that are the result of the alteration of pre-existing rock.
An example of that's like caves in Ohio.
Example of metamorphism? Or?
Yeah.
Example of metamorphism would be mountain building can cause metamorphism, hot chemical fluids can cause metamorphism, cold rock coming into contact with hot magma can cause metamorphism. Metamorphism is kind of like plastic surgery for rocks. It can cause very minor changes or very drastic changes. And those changes are caused mostly from increased temperature or pressure or both. They can cause changes to the rock's texture, its internal structure, and its composition. And if you're going to change all that, then you've got something different. Look at that. A very common metamorphic rock include marble, slate, gneiss. Gneiss shows up a lot as countertop and monument stone. A lot of your countertops are marketed as granite. The word granite means something very specific to a geologist. To a stone cutter, it means a rock with big crystals that polishes well. That's it. That's as far as they go. And then after that is where they come from. It came from Peru, it came from Mongolia, it came from Nova Scotia. That's all that matters. Any other questions? Now, all of these three rock types, this is what the Earth has. The Earth's not getting bigger or smaller, it's just constantly recycling the materials that it already has. And this process is known as the rock cycle. And that's shown in interlude A. Have a diagram of that here somewhere. First one I wanted, I could never find it. Well, maybe they don't have an A. Maybe they have it. See, this is why I hate when they go to new editions, because things that you would assume were the same, but they change. And the editions change, but they kept the same. It should be on page 262. Why did they put it right here? Oh, it's an interlude C called The Rock Cycle. That's why I couldn't find it. There it is, yes, page 262. Page 262. Cycle meaning it constantly goes from one to the next, one to the next, one to the next. There's no start point, there's no end point. It's like double dutch, you just jump in and go. There's no beginning or end, it just goes around and around and around. Essentially, what the rock cycle is demonstrating is that given enough time, the Earth's got plenty of that, if you get the right sequence of processes, you can take any rock the Earth already has and transform it into any other type of rock. You can start with volcanic activity that produces magma, that gives you an igneous rock. The igneous rock's exposed on the surface. It becomes broken into pieces. The pieces end up becoming parts of the sedimentary rock. The sedimentary rock is buried during mountain building. Gets squeezed and heated, becomes a metamorphic rock like a quartzite. The quartzite gets remelted, comes back up as another granite. It just goes around and around and around and around. It goes around, comes around. You can have sedimentary rock can be broken into pieces and become another sedimentary rock. You can metamorphose a metamorphic rock 2-3 times over. Like I said, metamorphosis is a lot like plastic surgery. You can go in and fix your nose, and then wow, yeah, that looks nice. And then go in and have your chin done, and then and then go in and have your eyes done, and then go in and have shin implants, and then go in and have something else lifted. Metamorphism can do the same thing. You can get a slate as a metamorphic rock, and then that slate can be heated again under higher temperature and become a schist. And then that gets heated again under greater pressure and becomes a gneiss. So that's the rock cycle. You can have an igneous rock, like a lava flow, a salt. And if it gets heated and remelted, it can become something else. Another igneous rock. It just goes around and around and around and around and around. Any rock has the potential to become any other new type of rock, given enough time and the right sequence of processes.
Is that like what they would be trying to accomplish if they did terraforming like on a different planet? Try to do something like facilitate that to happen?
Ultimately, I think it wouldn't necessarily be rock cycle, because on a lot of planets that simply would not be possible because they have no plate tectonics. Like, for example, Mars. The Mars core is cold. It's solid. There's no heat circulation. That would have to be, anything like that would have to be completely man-made and man-maintained. So you'd have to have some technological processes that would maintain that artificially. But to that end, your primary thing is definitely, you have to have some sort of carbon dioxide regulation to maintain climate and plant growth. You have to have some kind of system to maintain water in the atmosphere, to get precipitation,
Some kind of
soil development.
Internal heat source that would have some of the plants.
Well, see, that's the thing. And Mars, presumably, there are water-borne features on Mars. There's sedimentary rocks on Mars. So, we had flowing water on Mars at one point. We had volcanism on Mars at one point. So, it did have a hot interior. It's a smaller planet than we are. So, by whatever means that aren't yet fully understood, their core cooled much faster than ours did. But yeah, without that internal furnace, there's no natural process to keep it going on its own. It would need life support, like being brain dead. It's got nothing on its own. That's an interesting way to look at Mars. The brain dead planet. I think we have enough problems with this planet before we go messing up another one. We'll probably fix these problems first. If that fails, we need a fallback. Right? So, igneous, sedimentary, metamorphic. Are there any questions? For the next several weeks, you're going to learn more about rocks and minerals than you ever really wanted to know. But they're vital to our everyday life. Even if we go to another planet, everything we take with us has to come from this planet. Geology is an everyday part of your life, from the clothes you wear, to the food you eat, the air you breathe, to the car you drove or the bus you drove here, your books, your jewelry, your cell phone. All of that came from the earth. It's all manufactured from materials from the earth. The average home is between 300 and 500 tons of rock in the average home. That's everything from the cement to the concrete, the foundation, for the asphalt, the roof shingles, and at least 300 to 500 tons of rock per home. Had to be located, had to be mined, had to be processed, had to be shipped, had to be trucked in. State of Ohio is the top 5 producer in the nation of sand and gravel for construction. Thank Glaciers for that. We export sand and gravel to China. Do you know that?
Oh my gosh, we sent something.
We sent something to China. Yeah. They have a lot of limestone over there, so they have that part of cement. They don't have a lot of the sand and gravel part. So we send them sand and gravel, yeah. Now what's heavier? A big box of jeans and shirts, or a boatload of gravel? Yeah, I think it all works out. Yeah, you send us a few boxes of 50-cent T-shirts, and we'll send you this box of $400 gravel. Okay. Yeah, that works out.
And so when you take vitamins and quote-unquote minerals, what does that mean exactly, the minerals?
The minerals that are in reference there are primarily elements. It should be vitamins and elements. But when you take like Centrum, that's man-made, it's manufactured. So the raw materials to make that pill, the iron, the calcium that's in that pill, the zinc, came from this and that, this and that. Yeah. So in that sense, they're minerals, and that's their ultimate origin. They've been mined for that purpose. Yeah. That's what makes some of those supplements really expensive, because not all of these elements are equally abundant. Yeah, and if they have other industrial uses, that uses that is a higher demand, so then what's left is more expensive. Yes? Yeah. Quartzite.
Isn't amethyst made out of that?
Amethyst is a variety of quartz mineral. It's purple quartz. And you can have, they're not that common, but you can have purple quartz sandstones or amethyst sandstones made of little tiny purple sand grains from amethyst crystals. And that can get metamorphosed to give you purple quartzite.
So it's not that amethyst is made out of quartzite, it's just...
Amethyst is quartz.
Yeah, it's just a type of...
It's a type of quartz that can be in a quartzite rock.
So it falls under the metamorphic rock?
Mm-hmm.
No?
No, it's a mineral.
Oh, okay.
It's a mineral that can be found in that type of rock. Does that answer your question? It's kind of like brown is a type of sugar that can be found in certain cookies. It's all in the ingredients. I mean, you laugh, but it's the same thing. These are the ingredients, and that's what's made with them. Yeah, quartz comes in all kinds of crazy colors.
You're hungry a lot when you're in here. All your references.
Food is what I relate to. It is kind of lunchtime. You're going to kill me because I got other food references that we can eat this wrong. Any questions? That's good for you. Well, they gives you some ideas on what to get for lunch. Yes?
Does diatomaceous earth that like that, does that happen then?
Oh, the diatomaceous earth is it's made of diatoms. That helps a lot, doesn't it? Diatoms are microscopic plankton that they make these beautiful ornate, very delicate, you can only see them on a microscope, these really ornate, lacy, delicate shells out of the quartz. And what happens is when they break, there's just like shards of broken glass at a microscopic level, and that's why it kills bugs, because it literally slices them up.
Oh, it really works, huh?
Oh yeah, it works. It works. It works really well. Bugs walking through that is like you walking through broken glass barefoot. Barefoot and naked. It just chops them up. Yeah. I wouldn't recommend it. Die, ants, die. It's really good for ants. Okay, well, submit your questions.
Why would you recommend it?
Because it works really well. It's quite effective. You gotta keep your pets out of it. You don't want your dog or cat licking it off the floor. Because it's basically glass. It's really sharp. So, igneous rocks are what we're going to start with. So, we're going to start with igneous. So, we start with the definition. From the cooling and eventual solidification of molten rock. First of all, we need to know and have a firm understanding of molten rock. Molten, as a word, is not the same as melted. Melted implies that it's all liquid. Like you take a stick of butter, and you put it in the microwave, and you go, and then you get a bowl of liquid, pourable butter. That's a melt. Molten describes a material that's mostly liquid, but with lumps, but with incompletely melted lumps. Yeah, you're not going to be happy with me.
Like cottage cheese?
Like what?
Is it like cottage cheese?
Can be.
But hungry?
Yeah, can be. Very wet cottage cheese. Yeah. Only hot. Not, cold. Okay. Where are my Rice Krispie treat makers? My Rice Krispie treat eaters? People that have seen Rice Krispie treats being made, is that a general process? You start with a skillet or a big pot or a pan. Everyone, if you make Rice Krispies, you eventually find the pan. You know what I mean? The Rice Krispie pan. It just does the best. You melt the butter, which means the butter goes in and it's liquid, right? Then you put in the marshmallows. Well, you have to stir while the marshmallows are melting. Cut them up into small pieces, they'll melt quicker. Your knife gets really sticky. And you have to stir because one, you need them to melt, but you don't want the marshmallow to burn. So you stir. You're going to reach a point where it's mostly liquid, but there's still these few lumps of marshmallow still in there. You know what I mean? And you're like trying to squeeze them with the wooden spoon and spatula, get a smooth to melt. Nice. You want to put the Krispies in it? That is your molten state. Mostly liquid, but with incompletely melted lumps. Sometimes it's melted enough. I'm putting the Krispies in. It will melt while it cools. That's molten. If you're making fudge and you got it ready, you get it to the boil and it's at the soft ball stage, and then you want to add some chocolate, like mini morsels. Okay? And you got to stir, and you're waiting for that to gloss over and for all the little lumpy bits of chocolate chips to finish melting. That's a molten state. It's a molten state. So that is what molten rock is. It's mostly liquid. The liquid portion is called the melt. But the rest of it's lumpy. Incompletely melted lumps of rock, new minerals in the process of just forming, parts that are a little lower temperature that are still kind of chunky. That's a molten state. One of my favorite questions. Anybody?
Is it blocking up there?
Thinking too hard. Good start, thinking too hard. What did you say? Thinking too hard. Thinking too hard. Anybody? You're laughing in the back. You know it. You know it, no? You can smell the concentration in here. Okay, let me ask this question. Where does molten butter come from? Where do you get melted butter? Okay, the lobster's out of the pot, and you need the melted butter to go with crab legs. And those. Where does the melted butter come from?
Microwave or the stove.
If you're going to make your own melted butter,
Put it in the pan, you melt it.
you melt what?
Butter.
Butter. Solid
Rock.
butter. Where does molten rock come from? Solid rock. It's such a simple answer, it's stupid. Where does molten rock come from? Solid rock. Solid rock that gets melted.
You should have that.
No, that's okay. Solid rock that gets melted. We have there's a chemist, Mick Canistero. He's a weekend stand-up comedian. He's pretty good. He's kind of funny. He's one of the departments in there. Solid rock that gets melted. It's stuff you already have. The earth isn't let anything away. So, gee, I need molten rock today. So it's, well, I have this rock and this rock. It'll just use whatever it's already got. That's part of your rock cycle. So now, how do we melt rock? What do we need? Hold on, let me write it on the board. As fast as I can. Okay, what?
Pressure and heat.
Well, definitely, I heard heat for sure. I mean, you need temperature higher, right? For sure, higher temperatures. Now, where do we find higher temperatures? At the surface or underground? Underground. So, most of your molten rock is not forming here at the surface. It's forming underground. It needs a higher temperature. Most rocks don't even start thinking of melting until they get up to about 400 or 500 degrees Fahrenheit. There's some minerals that don't melt at 2,000 degrees. So, they're going to be really, I'm loving that. They're going to be really, really fun. Well, think about it. You ever seen movies or TV shows or documentaries where they're like in a steel foundry, they're making steel? They have those big things and they're tipping it over, the molten steel coming out. Cool, right? You ever think, what the hell are they holding that in? But you can't put it like in a Tupperware container, right? Right? So what do they put that liquid steel in? It does not. They make those things, those crucibles, out of minerals that form at temperatures much higher than the melted steel. So they don't melt. They're very expensive. They don't melt.
Same concept as like in the old days when they used to make swords.
Yeah. A high temperature, you go deeper into the earth. Now, there's a problem with getting deeper into the earth because temperature isn't the only thing that increases as you go deeper. Question?
So, did you find molten rock a lot when, like, a volcano erupts?
Yes. The is that a volcano is allowing the molten rock from deeper down to come to the surface. Does that answer your question? Something else that increases as you go deeper. Pressure. Now, you gotta come back to physics just a little. I know. There are three main states of matter. Right? You can have a solid, a liquid, or a gas. Okay. Right? Okay. That's physics, believe it or not. You already know that. It's amazing. Now, the only thing that's different between those three states of matter is how freely the atoms are able to move. That's the only difference between the three. So, for example, in a gas, like the air in this room, the atoms in that gas can move wherever they want, up, down, sideways, over here. I'm going to go over there, let's go up here. No, they can go anywhere. In your lung, out your lung, around, and somebody else's lung, out, down, around again. Okay. In and out, they can go wherever they want. Okay. To be a liquid, the motion of the atoms is a little more restrained than that. They still have freedom of movement, but they don't quite have the same freedom of movement as a gas does. For example, if I turn on this faucet, I'll get there eventually. That water is a liquid. It's flowing freely out of the faucet and down the drain. But it's not going everywhere into the room like the air is. It's a liquid. Still, the motion of the atoms is a little more restricted than it is in a gas. That's why it's a liquid. When we come to a solid, the atoms in a solid are even more restricted in their ability to move. Now that can be difficult to imagine, because from the time we're this big, we were talking, solid. But if you were to look at the tabletop at a microscopic level, at an atomic level, all of the atoms that this tabletop is made of are doing this. They're moving. They're not moving very much because they're restrained. They're just kind of like, but this whole table's quivering. But you can't see it. You can only see it at an atomic level. And this, I don't know about you, but that was like really freaking me out. So I'm kind of glad that I can't see it. Because this whole building's just going. And that's just weird. Bizarre. You're going, little atoms are moving. Oh, there was like this window. So that pressure will keep things solid. Pressure will keep those atoms from moving freely. So the deeper you go into the earth, the greater the pressure becomes. And you can have rocks that are 2 to 3 times their melting point, but they stay solid because the pressure will not allow the atoms to move. It's kind of like being in a really, really crowded nightclub where all you can do is this, right? And it's like 800 people, and you're like, God, it's hot, I'm going to pass out. And you try to pass out, but you stay standing up because it's so tight together, you can't fall. That's what's happening. So in addition to having a higher temperature, we need to drop the pressure. This is what happens at a divergent plate boundary. At a divergent plate boundary, plates are separating, they're pulling apart. As they pull apart, they release the pressure on the rocks that are underneath. And with that release of pressure, those hot rocks of the upper mantle and the asthenosphere will melt in an instant. That produces molten rock. It drops the pressure. This is referred to as decompression melting. You can think of it this way. The atmospheric pressure, 14.5 pounds per square inch-ish, pushing on you right now keeps all of you together. If I suddenly put you in a vacuum and decompress you, all of your atoms would move along more freely. No. We all laugh and go, oh, cool, and then we're like, oh, they're there. So decompression melting. You can drop that pressure, those really hot rocks will be able to melt because their atoms will be able to move. How else can we melt a rock? Well, we can add fluids. Especially water and gases like carbon dioxide. Water will lower the temperature for melting. Water, especially when it gets hot and turns to steam, is a very powerful substance. As hot steam under pressure, water has the chemical ability to invade the crystal structure of minerals and actually dissolve, break apart the bonds that hold the atoms to each other. So once you can get the atoms separated from each other, they're more free to move. So adding water and other fluids like carbon dioxide gas makes the rock melt, or allows the rock to melt at lower temperatures. So it facilitates the melting. We'll see this happening especially at subduction boundaries, where the ocean floor is subducting back into the mantle. That ocean floor is an intersubduction. That oceanic crust is not just bringing rock back with it into the mantle, it's dragging a lot of ocean water down with it. Water that seeps down into the rocks over time into all the cracks and crevices, water that's soaked into the sediments that are on the ocean floor. All of that gets dragged, it's like dragging a sponge back down into the mantle. As soon as that water heats up and starts to boil and become steam, that steam goes to work, breaking apart all the chemical bonds and the minerals, and everything melts and comes back up. And last but not least, we have to look at the mineral composition. Different minerals form at different temperatures. Different elements have different chemical and physical properties. They may not like each other at different temperatures, but you get them too hot or too cool, and oh yeah, okay, and then they can bond together and form compounds. So all of those 4,000 minerals, they form at different temperatures. If they form at different temperatures, that also means they melt at different temperatures. Anyone here trying to do the low-fat thing? You ever try that low-fat, no-fat cheese slices? You ever try? Don't. They're so gross. You get like a couple of the Velveeta slices, and you make a nice, grilled cheese sandwich. It's all gooey. Some tomato slices with some bacon. But then if you use those other no-fat, low-fat cheese slices, it just goes to water in the pan. Just try it. It's gross. The reason why they melt so differently, no fat. That makes a huge difference. Yeah. So it's a different composition. So it has a different melting temperature. The fats in the real cheese melt differently than whatever it is in the fake cheese. It's the same thing with minerals. Minerals make up rocks. If you have certain minerals in the rock, then those minerals will determine what temperature you need to melt. Now, are all rocks created equally? No, they don't have constitution. So, some minerals will be in some rocks, but not in others. Different rocks are made of different minerals. So not all rocks are going to melt at the same temperature. Some rocks melt at low temperature, some at medium temperature, some at high temperature. What temperature is necessary depends mostly on what minerals are present. Some rocks only partially melt. Only those minerals that can melt at that temperature will melt out. The rest of the rock will stay solid. Are there any questions? That's a good place to stop. That's a good place to stop. Question?
What's the hardest type of rock? Like,
Hardest type of rock? There are a couple that are really, really difficult to get through. One is quartzite, because quartz is a very dense mineral, and it's got a hardness of 7. So you pretty much need a diamond saw